the rotating magnetic field in induction motor. Okay, so there we saw how when we apply the three-phase supply to the stator, and when three-phase currents are drawn by the stator winding, we get a three-phase flux operating in the same space, that is in the same air gap, and when those three fluxes will interact each other, how we get a rotating magnetic field with respect to the change in the omega t value of the supply voltage. Okay, so because that rotating magnetic field is existing in the motor in synchronous with the supply angular frequency omega, we call or we say that the speed at which the rotating magnetic field is rotating in the induction motor as the rotating speed. So the synchronous speed. Okay, so what is happening exactly there? We have an induction motor. Okay, so this is induction motor we have, so on. This is the rotor. Okay. And when I supplied three-phase supply to this, I got three-phase flux phi A is equals to phi m sin omega t, phi B is equals to phi m sin omega t minus 120, phi C is equals to phi m sin omega t minus 240. So these three fluxes when existing in the same air gap, the three-phase waveform is R, okay, Y, and B. So when these three fluxes are existing, this is phi A, phi B and phi C. Okay, at any instant you consider, okay, this is 0, 90, 180, 270, okay, 360. You consider any time instant. Okay, so at this time instant, okay, which is around just greater than 120 degrees, phi A is existing, phi B is existing, phi C is existing. So these three are existing in the same space. Here I have phi A, here I have phi B, and here I have phi C. The direction of phi A, phi B and phi C and their magnitude depend upon the value of omega t. Okay, and at what omega t, what is the value, we can get it by substitution. So what we see here is there are three fluxes phi A, phi B, phi C. Either it may be phi A plus phi B minus phi C, phi A minus phi B plus phi C, phi B plus phi C minus phi A, whatever combination depending upon its value. Now with respect to this here, phi A is positive, phi B is positive, phi C is negative. So the total flux will be phi A plus phi B minus phi C. When these three fluxes are existing in the same space, like I explained in one of the previous class, that when two magnets or multiple magnetic fields are interacting at the same space, I get one resultant field, and that resultant field will be having the capacity to do the work. The same thing is happening. So because of interaction between, okay, these three fluxes, because of interaction between these three fluxes, I get a resultant flux called phi r, and this phi r is equals to 1.5 phi m. The magnitude of the resultant flux is always 1.5 times the maximum flux phi m. So this is phi m, this is phi m, this is 5. Okay, so 1.5 times the 5m. Okay, and this is the resultant flux and not steady flux. It is an alternating flux, sinusoidally alternating flux, and also this resultant flux is rotating in nature. It is rotating in the space. So either it will rotate in clockwise direction or it will rotate in anti-clockwise direction, depending upon the sequence, phase sequence. Okay, so it is experimented and noted that if the phase sequence is A, B and C, the RMF rotates clockwise. If the phase sequence is ABC, that is RYB. If the phase sequence is RYB or ABC, the rotating magnetic field will rotate in the clockwise direction. It is observed in the lab. Okay, we have observed in the lab. If I want the opposite direction, then instead of ABC, I will make it as ACB. By changing the phase sequence, I can change the direction of induction motor. Okay, so that is the importance of phase sequence, which we studied in three-phase circuits. Fine. So this we have seen in the last class, that when I apply three-phase supply to the stator, three-phase currents are flown in the stator winding, which is distributed three-phase winding. Those three-phase currents will produce three-phase flux, phi A, phi B, phi C. When these three fluxes are simultaneously existing in the air gap, those three fluxes will interact with each other and they produce a resultant magnetic field of constant amplitude 1.5 times phi m. Okay, so what is when these three are added? When these three are added, I get a resultant magnetic field of constant amplitude. Okay. I will draw that with some other ink. Okay. So I will get a constant amplitude magnetic field. This is phi r, and this is equals to actually this is double the phi m, but actually it will be 1.5 times phi m. Okay, and please remember it will be in synchronous with supply, so it will be always varying with respect to omega t. So only I have drawn phi r in phase with phi a, not in phase with phi b or phi c. Okay, so when phase A reaches maximum, phi r reaches maximum. When phase A reaches 0, phi r reaches 0. When phase A reaches negative maximum, phi r reaches negative maximum. Okay, so whichever phase is starting at omega t is equals to 0, whichever phase is starting with initial phase angle 0, my resultant magnetic field phi r will be having in phase with that phase flux. Okay. So this is the resultant flux. So this is the resultant flux which is alternating in air gap and also rotating in air gap. So you can imagine a sine wave rotating in the air gap. I will show you in the next figure. You can imagine the sine wave rotating in the air gap, and what is the magnitude? It is this. This is 1.5. Okay, the amplitude is 1.55. It is not that always the magnitude value is 1.55 of the flux. The amplitude is 1.55, and what about the variation? It is alternating. Okay, it is alternating. So now, if you want to write the instantaneous equation for phi r is equals to 1.5 phi m into sin omega t. Phi r is equals to 1.5 phi m into sin omega t or sin theta. It is sinusoidal and also rotating. Okay, so this is the rotating magnetic field. Now when this exists in the induction motor, what is the effect that is causing the motor to run? We have to study. Okay, so next is principle of operation of induction motor. Principle of operation of induction. are the stator slots that carry stator winding. So this is the stator and we have the rotor. We have the rotor. Okay, so now we are applying the three-phase supply R, Y and V, and this three-phase supply, when I apply three-phase supply to the stator R, Y, V, this three-phase supply is creating a rotating magnetic field. It is creating a rotating magnetic field phi r in the air gap, and this rotating magnetic field is rotating in the air gap. Okay? It is rotating in the air gap. Now, when we go back to the construction of the induction motor rotor, we have seen that whether the rotor is slippering induction motor or squirrel cage induction motor, the rotor is always completely short circuited on itself. So in case of squirrel cage induction motor, there is very much evident that all the conductors in the slots are connected to end ring through bracing, and that will form a short circuited structure. So this is the squirrel cage motor. This is the squirrel cage rotor. What we have? We know that these are the conductors and these are the end rings. So when these conductors are braced at the end rings, okay, braced at the end rings here, this is forming a short circuit structure. This is made up of copper. Conductors or bars are made up of copper. So do you think that this is entire short circuit one? Definitely, it is a short circuit condition. Okay, electrically this rotor is under short circuit condition, and these conductors are placed inside the slots and slots are covered. So this is an internal skeleton of cage rotor. Okay, now when you take the slippering rotor also, this is the slippering rotor. I am placing number of turns in the form of winding in the slots, and those conductors are connected to these three slip rings. You can see these blue strips, these are three slip rings. So this, all the conductors, one slip ring for each phase. So all the conductors per phase are shorted to these slip rings, are connected to these slip rings. Okay, and these slip rings through carbon brushes are connected to the external resistance. Okay, if you see the construction, so these are the three slip rings. Okay, so winding will come here. From each phase, the winding is coming to slip rings, firmly connected, and through the brush arrangement, I am connecting these slip rings to external resistance. And these external resistance are short circuited. Now if you see the star connected winding in the rotor, this is usually star connected. Okay, the rotor of slippering induction motor winding is connected in star. So if you equivalently see, there is a star connected rotor winding. Okay, or little bit above. This is slip ring. Okay, so R phase of rotor, R phase of rotor, Y phase of rotor, B phase of rotor. The subscript R indicates rotor. Now I have three resistances connected. through brushes. Okay, and to these slip rings, these three connections are given. Now electrically, whether the rotor winding of the induction motor is short circuited? Definitely. Okay, this is R is connected to this R. Okay, this is R. So electrically this is short circuited rotor. Okay, and even in squirrel cage, you can observe these are the rotor bars, and each rotor bar is braced to the end ring. So there is a connection here. This will be connected to the other end of the rotor bar end ring. So this is the cage rotor. So in both the cases, rotors are electrically short circuited. Both the cases, rotors are electrically short circuited. Please keep this in mind. I need this point after a while. Okay. So now coming to what happens now. I have connected a stator. Okay. This is my stator. To this stator I have given the three-phase supply, and this stator is now producing a rotating magnetic field in the air gap. Now I will place the rotor here. It is difficult for me to create a uniform air gap. Okay. You please somehow I can manage somehow. Fine. Okay. Yeah. So here, this is the rotor. I have placed the rotor inside the stator. Now this is the exact motor structure what we get when we open the motor. Fine. When we open the motor, this structure we see. Rotor placed inside the stator cylinder. Now what is happening? I am connecting three-phase supply here, RYB. Okay, I am connecting three-phase supply, RYB, and this three-phase supply is creating a rotating magnetic field in this space, that is air gap. Space for me is air gap in any rotating machine. Space for me is air gap in any rotating machine. So it is creating a rotating magnetic field. Now observe, there are conductors in the slots. A magnetic field is rotating. What should happen? The flux that is linking to these conductors is rotating. So there is a generating action taking place. So there is a rotating flux that is linking to this conductor. What is happening? In this conductor, the flux that is linking to it is continuously changing. Therefore, there is a dynamically induced EMF in the rotor. Okay, in each rotor conductor, the rotor conductors will experience an induced EMF in it. They experience an induced EMF in it. Now, the moment EMF is induced in the rotor circuit, here or here in the conductors, okay? Because the rotors are short circuited on themselves, immediately current starts flowing in the rotor conductors, whether it is slippering or whether it is cage rotor. Okay, whether the moment the EMF is induced in the conductors, because of the short circuit condition of the conductors on itself or in the entire rotor, immediately current starts flowing in this conductors. Now, as per the principle of motor, when the current carrying conductor is placed in a magnetic field, that conductor has to experience a force. Now, the rotor is not free to move anywhere outside the construction. The rotor is always fixed to, at the end, you can see here, the rotor construction will be in such a way that these two ends will be fixed to stator through bearings. We will be using simple bearings, ball bearings in case of small machines, roller bearings in case of large machines. So at the both ends there are bearings. Inner race of the bearing is connected to the shaft, outer race of the bearing is connected to the stator. Okay, inner race of the bearing is connected to the shaft. This shaft, one shaft will come this side, and outer race of the bearing is connected to the stator. Therefore, whenever the force is exerted on this conductor, they are free to rotate but not move outside the stator construction. They are free to rotate, and when these forces produced in each conductor is in the same direction. Okay. Now suppose the force exerted on this conductor is towards right, your right, is towards right. Okay. The force experienced by this conductor is also towards right. Experienced by this conductor is also towards right. When all the forces exerted on the conductors are in the same direction, the rotor starts rotating. The rotor starts rotating like this. Okay. So this is how the force is produced in an induction motor. Because the current is carried by this conductor through induction process, it is called induction motor. Okay. Because the current is carried by these conductors, rotor conductors, through induction, there is no physical contact between the stator and the rotor. There is no physical contact between the stator and the rotor. Therefore, the current conducted in the rotor is through induction. Exactly the same principle of transformer. Now initially when the rotor is not yet rotating, it is a short circuited secondary of the transformer. Rotor acts like short circuited secondary of the transformer. Therefore, the principle of operation of transformer and rotor is same, mutual induction. But in transformer it is static induction, in induction motor it is dynamic induction. So transformer becomes static machine, induction motor becomes dynamic machine, though they both operate on the same mutual induction principle. Okay. So now how will be the conduction happening? Once again I will explain. Okay. I have given the three-phase supply to the stator. This three-phase supply is creating three-phase flux. That three-phase flux is interacting and resulting into the rotating magnetic field. Now each conductor is experiencing the change in flux, because this rotating flux, okay, which is rotating in nature, is rotating, and each conductor is cutting this flux. Therefore, the moment conductor cuts the flux, an EMF is induced in it. Okay. The moment conductor cuts the flux, an EMF is induced in it, and as the rotor construction is short circuited on itself, it starts circulating the current in the rotor conductors. Okay. So now there is a flux in the area. Now each conductors are also creating the flux. Okay. Each conductor is creating flux. Now these two fluxes will interact. The rotating magnetic field, that is the rotating flux, and the flux created by the conductors, rotor conductors. So these two fluxes will interact with each other, and there will be either attractive force or there will be repulsive force. Okay? And the force will be exerted in such a way that all the conductors will experience the tangential force. All the conductors will experience the tangential force. Why they experience tangential force is, the conductors are placed on the outer periphery of the rotor. Here. Outer periphery of the rotor. So when it has to rotate or it has to move, it has got only two options. Either it has to move clockwise or it has to move anti-clockwise. It cannot jump and come out because it has got a constrained construction. Okay, physical construction is fixed. So now the conductor has to rotate in either clockwise or in anti-clockwise. So when this movement has to happen, then the forces induced on each conductor has to operate tangentially. When this conductor experiences a tangential force, then only it can move. Okay, so it will move like this. is tangential to the radius, that is called torque. Okay. Now these are the conductors. These are the conductors. Suppose this is the conductor placed and it experiences a force at some radius. So what is F into R? Is nothing but my torque. So a torque is produced in the motor. We never talk in terms of force in the motors. We always talk in terms of torque in the motors. Why? Because motors are always operating with cylindrical structure. The rotor part of the motor is always a cylindrical structure, and always the rotor part is kept inside the stator part. There is one exception for this. One exception for a motor where the rotor is outside the stator is our ceiling fan. If you open the ceiling fan, you will get to see that the outer part is rotating, inner part is stationary. Okay? The outer part is rotating, inner part is stationary. Actually, what is happening in this motor? The part to which I am giving the supply is remaining stationary, and the part in which the force is induced is rotating. But in case of ceiling fan, the part to which I give the supply remains stationary, that is inside. Okay? If you open the ceiling fan, you will get to see the outer body is rotating, inner body is stationary. That is one exception what you can observe, where the rotor is outside the stator. Here the stator surrounds the rotor, there the rotor surrounds the stator in case of ceiling fan. Okay. So this is how an EMF is induced in the, a torque is produced in the induction motor. Okay. Three-phase supply is given, rotating magnetic field is produced. And one point we have I forgot to deal with. Synchronous field has got its equation. Okay. After this we will see that. What is synchronous field? We discussed already in the previous class. The speed at which rotating magnetic field is rotating is synchronous speed. Why it is called synchronous? Because the frequency of rotating magnetic field is equal to the frequency of supply. Therefore, it is in synchronous with the supply. The speed at which it rotates is called synchronous speed. That is what we have seen. Now, when three-phase supply is given, rotating magnetic field is produced. That rotating magnetic field is linking to the rotor conductors, and these rotor conductors are experiencing continuous change in flux. Because they are experiencing change in flux and EMF is induced in the rotor conductors, because rotor structure is short circuited, the current is circulated in the rotor conductors, and these current carrying conductors, when placed in the rotating magnetic field, they will experience a force, because these current carrying conductors will create their own flux, and the rotating magnetic flux will interact with each other and the force is produced. This is the principle of operation of induction motor. Okay. Now one question: if I don't short circuit, what will happen? If the rotor construction is not short circuited on itself, what will happen? The motor will not rotate, because there will be EMF induced, but there will be no currents flowing in the conductors. To flow the current, I need closed path. Okay. So if any of the phases are open, then there will be an EMF induced in the rotor conductors, no doubt, because of the rotating magnetic field. But because of incomplete path for the flow of current, the current existing in the rotor will be zero. There is no current existing in the rotor. Hence, to produce force, I need current, because F is what? F is equals to BIL sin theta. So I need current, I need flux, I need conductor. When all the three are existing, then only I can get the flux. If any one of these three is not present, then my conductor will not experience the force. Okay. So this is the principle of operation of induction motor. Now the question comes is, in what direction the induction motor rotates? Now I told, with a phase sequence of RYB, I am firmly telling this because we see in our lab, when the phase sequence is RYB from the supply, the induction motor rotates in clockwise direction. Okay. So when phase sequence is R by B, my rotating magnetic rotates in clockwise direction. When phase sequence is R by B, my rotating magnetic field will rotate in clockwise direction. Then in which direction the rotor should rotate? In clockwise or in anti-clockwise? There are only two options. It has to rotate in clockwise or in anti-clockwise. The question is, this is the question, whether it rotates in clockwise or it rotates in anti-clockwise. Okay? The rotor will always rotate in the direction of rotating magnetic field. If the rotating magnetic field or RMF is in clockwise direction, the rotor will rotate in clockwise direction. If the RMF, rotating magnetic field, is in anti-clockwise direction, the rotor will also rotate in anti-clockwise direction. Now the question, why so? Why the rotor rotates in clockwise if RMF is in clockwise? Why not rotor will rotate in anti-clockwise if RMF is clockwise? The answer for this is because of Lenz's law. Answer for this is because of Lenz's law. Now what does Lenz's law states? Lenz's law simple states an induced EMF always opposes its own cause. Then the question is, there is a force induced, why the EMF has come into picture? That is the question. Okay? If you see the profoundness of the Lenz's law, we have studied so far the Lenz's law only for the induced EMF. Okay, whether dynamic or whether static. But there is generality of Lenz's law that anything that is induced electromagnetically will oppose its cause. Whether electromagnetically induced there is an EMF or a current or a flux or a torque or a force, whatever. If anything that gets induced electromagnetically, it will oppose its cause. Now, the end product of the induction is force or the torque. But what is the main cause for the production of torque? Main cause for the production of torque is current. What is the cause for the production of current? This is the EMF induced. What is the cause for the production of EMF induced? Rotating magnetic field. If magnetic field produced will not rotate, the EMF induced in the secondary conductors or the rotor conductors will be zero. So the main reason for EMF induction in the rotor is rotating magnetic field. Therefore, the force produced by the rotor or the torque produced by the rotor will oppose the rotating magnetic field. So what it tries to do, oppose means what? It will not stop with its hands to just drag back and hold it to stationary position. It can't do that. It will try to reduce the relative motion between itself and the rotating magnetic field. Now the EMF induced in the rotor conductors is purely due to relative speed. It is purely due to relative speed. Now the conductors are stationary. Initially, let us assume the conductors are stationary. The magnetic field is rotating. Conductors are stationary, magnetic field is rotating. So for example, I will take one paper. Yeah. So which long back I had taken in your class. Luckily it is preserved. Yeah. Now this is my conductor. I will take this. This is my conductor. Okay. This is a magnetic field. Now the conductor is stationary. Conductor is remaining stationary. You can observe this black dot is my conductor. Conductor is remaining stationary and rotating magnet is rotating. Okay. So therefore you can observe when the rotating magnet is rotating, the scope is very less, please bear me. Okay. When the rotating magnet is rotating, linking to the conductor, at every instant the conductor is experiencing the change in flux. This is because of this reason an EMF is induced in this conductor. because of change in position of the magnetic field. Because magnetic field is rotating and is linking to this conductor, the conductor is experiencing continuous change in flux. Therefore, an EMF is induced in this conductor. Now suppose both conductor and magnetic field rotate at the same speed along with each other. Now conductor is in the magnetic field, but the conductor and the magnetic field both are rotating simultaneously. Now do you see any change in flux or flux cut by the conductor? No. Is it? When the relative speed of the conductor and the rotating magnetic field becomes equal, when the speed becomes equal and this relative speed becomes 0, both will be operating at the same speed or running at the same speed. So when the conductor is rotating at the same speed, okay, the relative motion is 0. Therefore, the flux cut by the conductor is 0. Hence, the EMF induced in this conductor is 0. Current produced in the conductor is 0. Force produced in the conductor is 0. It means that conductor will not rotate. Rotor will not rotate. To reach this point, this rotor always tried, because it has to oppose the cause completely. If you take a static induced EMF in a coil, the total EMF induced in a coil in a pure inductance with no resistance in between, the induced EMF in a coil is exactly equal to supply voltage. The net voltage becomes 0 there because of Lenz's law only. But here, because of this speed of the rotating magnetic field, there is an EMF induced in the conductor. Okay? So there in static induced EMF becoming equal to supply EMF. Here, the induced speed tries to become equal to the rotating speed of the magnetic field. Okay? Therefore, to achieve this, it tries to rotate, or it will rotate in the direction same as that of rotating magnetic field. Now what happens if it runs in opposite direction? Relative speed increase, induced EMF increase. But as per the electromagnetic induction, okay, the opposition has to occur wherever there is an induction occurring. Okay, that will be against the principle and nature of the induction, electromagnetic induction. So therefore, the conductors will try to take the direction along the direction of RMF so that they can oppose the induction, so they can reach the speed of the RMF, rotating magnetic field, and make the induction 0. Now what happens if this occurs? Now suppose the conductor is induced its EMF, okay. Now the speed at which the rotating magnetic field is rotating is synchronous speed. Now there is the speed of rotor also. Exactly, it is difficult to show because synchronizing two hands it takes a lot of practice. Okay? So this is rotating at larger speed, this is rotating at some speed. Now still there is a cutting of EMF. Now if these two speeds achieved are same, if these two run at the same speed, then what happens? Flux cut by the conductor is 0, EMF induced in this conductor is 0, force produced, current flowing is 0, force produced is 0, rotor stops immediately. The moment rotor reaches the synchronous speed, the rotor stops. Okay? Then the question is, will ever the rotor reach synchronous speed? The answer is no. Rotor of induction motor will never reach synchronous speed on its own. It will always try to reach that speed, but it will fall back. It will slip down the synchronous value. Why? Because induction process is continuously happening. Therefore, always there is a torque produced, and that torque produced is trying to oppose. Therefore, the speed produced by the rotor is always lesser than the synchronous speed. Hence, the induction motor tries to reach the synchronous speed, but it will fail and fall back and slip back. Hence, the difference of these two speeds, the speed at which the rotating magnetic field is rotating, that is synchronous speed, and the speed at which rotor is rotating, is called slip speed or relative speed. Okay, slip speed or relative speed. Why rotor rotates in the direction of RMF? To oppose the induction of force, to oppose the induction of torque. Why the torque is induced? It is induced because of current. Why the current is induced? It is induced because of EMF. Why the EMF is induced? It is induced because of the relative motion between the conductor and the magnetic field. If magnetic field is not rotating, then this induction motor will not operate. If relative motion, if the magnetic field produced is not rotating, then induction motor will never operate. Because the magnetic field is rotating, there is an EMF induced in this conductor. Because EMF is induced in this conductor and the rotor is shorted, the current is flown in this conductor. Because current is flown in this conductor, force is produced on this conductor tangentially, and the effect is the torque production. So this torque produced or the force produced has to oppose its main cause. Main cause is relative motion between the rotating magnetic field and the conductor. The moment it gains the force, it tries to oppose that force. It tries to oppose that relative speed. Hence, it starts rotating along the direction of rotating magnetic field. Now you know that when two bodies will move in the same direction, the relative speed is 0. With the same speed, the relative speed is 0. If n1 is the speed of one body, n2 is the speed of second body. If both are moving in the same direction, the relative speed is n1 minus n2 or n2 minus n1. And if the speeds are equal, then they are with respect to each other stationary. Okay? Then they are with respect to each other stationary. Okay? And whenever we are explaining the relative motion, we never fail to take an example of the burning train movie example. If you see the burning train, one train will be burning, but the people have to be transferred from the burning train to the good one. Then another train will be taken into the parallel track. That train will be run at the same speed of the first train. So when two trains will be moving at the same speed, these two are stationary with respect to each other. Then the people will be transferred from one train to other train. The people are saved. So when two bodies rotate at the same move in the same direction, relative speeds are opposing to each other, or net relative speed is one minus the other. When they are opposing in direction, one is coming opposite to the other, relative speeds will add up. Okay, if n1 is the speed of one body coming this way, n2 is the speed of body coming in this way, the relative motion will be adding up n1 plus n2. When they are rotating or when they move in the same direction, relative speed is n1 minus n2. So to oppose the relative speed, the relative motion, the rotor has to rotate in the direction of rotating magnetic field. But it will never try to achieve the speed of RMF. The rotor will never, it will always try to achieve the speed of RMF, but it will never achieve the speed of RMF. It will always slip back, and that speed is known as slip speed. The difference between rotating magnetic field speed, that is synchronous speed, and the rotor speed is known as relative speed or slip speed. Okay? So we'll see. Dictating these all points is difficult online. I repeated multiple number of times this explanation. Calmly you can watch this video and make your running points. Okay? So I will write a points if you want. What happens starting from giving the supply. Okay, first point. 3-phase supply. is produce three-phase fluxes. Okay, these three fluxes interact in air gap and produce resultant flux which is rotating. And produce resultant flux which is rotating. The rotor conductors cut the rotating flux. Rotor conductors cut rotating flux and EMF is induced in them. Okay, then since rotor circuit is short circuit, circuited, rotor conductors carry current and produce their flux. Now these current carrying conductors rotor conductors placed in rotating magnetic field experience tangential force. And rotate and start rotating in the direction of rotating magnetic field and start rotating in the direction of rotating magnetic field. The rotor rotates along direction of RMF to oppose the cause that produced rotation as per Lenz's law. The reason for or the cause for production of rotation or force is the relative motion between rotating magnetic field and rotor. Relative motion between rotating magnetic field and rotor. Hence rotor rotates in same direction as that of RMF to reduce the relative motion. In this way, it opposes. The cause of. In this way, it opposes the cause of production of rotation. Cause of production of rotation. Rotor always tries to achieve the synchronous speed of RMF, so that it completely opposes the cause of production of force or rotation. But it fails to achieve synchronous speed, and always falls back and slip behind the synchronous speed of RMF. Okay. Thus, the speed difference between synchronous speed and rotor speed is known as slip speed or relative speed. Slip speed or relative speed. Okay, and is given by slip speed S is equals to ns minus n. Slip speed S is equals to ns minus n, where ns is synchronous speed, okay, and ns is equals to 120 into F upon P. This equation we had to see in the last class, but at the end I had dealt this with, but because of the memory full of the recording device, last one point was not recorded, where it was just ns equal to 120 f by p. I had to write in that. Okay, so ns is equals to 120 f upon p, depending upon frequency and number of stator poles considered. And where n is, it is an rpm, revolutions per minute. When is rotor speed in rpm, rotor speed in rpm. But generally we don't represent slip speed in rpm, we represent it in percentage slip. Generally we consider percentage slip for any induction motor, and is percentage slip S is equals to ns minus n upon ns multiplied by 100. ns minus n upon ns multiplied by 100. Okay, so the rotor will never try to reach the synchronous value, it will always slip back. That percentage is given as ns minus n upon ns. So this is the percentage slip, and this percentage slip value is very important for my operating characteristic calculations of induction motor, which is obviously you don't study here, but in the higher study of the induction motor, analytical study of the induction motor, the slip plays very important role in the operation of induction motor. So therefore it is very important to consider. Okay, so this is all about the operating principle of the induction motor. Okay, so in the next class we will solve few examples based on the frequency, synchronous speed and the slip speed. Then we will move to the starting mechanism of induction motor and necessity of this starter. Okay, so we will end now the today's class. In the next class, tomorrow's class, okay, we will solve few examples on induction motor. Okay, and after that we will see on the starter and we will close this, and then we will start with the DC machines. Okay. So thank you for joining the class.